Hi friends, I am Selvan from Unit Chemistry. This is a continuation of previous presentation of term symbol. In this presentation, I am going to discuss the microstates and their calculation and how all possible term states are deduced in addition to the method discussed for deriving ground state symbol already discussed. Now I go to the presentation. What are microstates? All possible arrangements of electrons in a set of orbitals with slightly different energy is called microstates. The simplest DN system is D1, for which the term symbol is D. This state has no excited term. In this system, one electron in d orbital can be arranged in 5 different ways with ms value plus 1 by 2. The same electron can be arranged in another 5 different ways with ms minus 1 by 2. The number of microstates for D1 system as given in this diagram. The number of possible arrangement for D1 configuration is 10. So each arrangement is called a microstate. All 10 microstates are degenerate, that is, they are equal in energy. So the left hand side with the ms value plus 1 by 2, there are 5 different arrangements. The right hand side, there are another 5 arrangements with the ms value minus 1 by 2. So 10 different ways we can arrange one electron in the d orbitals. So there are 10 microstates. Each one is known as a microstate, and totally there are 10 microstates. The total number of microstates for ground term can be calculated by the formula 2L plus 1 into 2S plus 1. For D1 system, it's a doublet D. L is equal to 2 for D state. S equal to 1 by 2 for only one electron. Then, by applying this formula, 2 into 2 plus 1, 2 into 1 by 2 plus 1 is equal to 5 into 2 is equal to 10. So, this is a formula we can use to get the for a ground state term to find out the microstates. Now we see the number of microstates for D2 system. The ground state term symbol for D2 is triplet F. By using that formula 2L plus 1 into 2S plus 1, the microstates for D2 ground state term is determined as follows. For a D2 system, it's a triplet F. The L value is equal to 3. So now 2 into 3 plus 1 into 2 into 2 electrons are there. So the spin value is 1 by 2 plus 1 by 2 is 1. So 2 into 1 plus 1, that is equal to 7 into 3 is equal to 21 microstates for triplet F. But actually for the D2 system there are other excited term present. So that must be determined by some method is known as hole formalism. Now the determination of all possible terms for D2 system. The method is known as hole formalism. There is a pigeon hole method. This method is applied to determine the energy states of an electronic configuration. The empty orbitals are considered as positive holes and presented as box diagrams in which the electrons are added. It involves the arrangement of electrons in the prescribed orbitals given as boxes in all the different possible ways. The following rules are adopted to construct the diagram. One horizontal row is used for each value of ml. The first electron is placed at the highest ml value with the spin up in a given column. The second electron goes to the same column above the first electron. In subsequent columns, the electrons are placed systematically in higher rows until all possibilities are exhausted. The Pauli's exclusion principle must be obeyed. Now we see for D2 configuration the possible spin alignment of 2 electrons. So the 2 electrons can be aligned in parallel spin or anti-parallel spin as given. So these 2 electrons, the S value will be 1 for parallel and 0 for anti-parallel. So now the spin multiplicity is 2s plus 1 will be, if s equal to 1, it is a 2 into 1 plus 1 is equal to 3, there is a triplet. If s equal to 0, then the 2s plus 1 will be equal to 0, that is a singlet. So there are 2 states, triplet state and a singlet state. First we deduce the possible terms for triplet arrangement. That's a parallel arrangement using hole formalism as follows. Now you see here, the box diagram is shown here. The first left hand column shows the ML values of d orbitals. There are 5 d orbitals: dxy, dyz, dxz, dx squared minus y squared, and dz squared. They are given in the ML values, the left hand side, as plus 2. The ML values are given as plus 2, plus 1, 0, minus 1, minus 2. Now for this D2 configuration, the 2 electrons are placed in parallel spin in all possible ways as shown in the diagram. According to the rules, the first electron placed in the highest ML value in the second left column. You see here. So this is the first electron is placed in the first highest ML level. This is a plus 2. The second electron goes above the first electron in the same column. This is the second electron. The second electron goes in the same row above the first electron, the same column. In another arrangement, by keeping the first electron in the same level, the second electron placed in all other ML levels successively. You see here. Now the second arrangement, keeping the first electron in the same plus 2 level, the second electron goes to the next higher level 0. And again the third arrangement, keeping the first electron in the same plus 2 level, the second electron will go to the minus 1 level. And the fourth arrangement, by keeping the first electron in the same plus 2 level, the second electron goes to the minus 2 level. So the all possible arrangements keeping the first electron in the plus 2 level is completely exhausted. Now we start the first electron from plus 1 level. Next the second electron goes to the next higher level, that is 0, next high level. Then next, keeping the first electron in the same plus 1 level, the second electron goes to minus 1 level. Again we keep the first electron in the same plus 1 level, the second electron goes to minus 2 level. The 3 possible arrangements are exhausted. Next we keep the first electron in the next higher level 0. The second electron goes to minus 1. By keeping the first electron in the same 0 level, the next electron goes to the minus 2 level. The last arrangement is the next higher level is the minus 1. The first electron is placed here. The second electron is placed in minus 2 level. So the all possibilities keeping the electrons in the parallel spins, that is a triplet. The triplet arrangements are completely exhausted. Now we see the ML values. We find the ML values here. So there are 2 electrons, 1 into 2, 2 plus 1 into 1, 1. So 2 plus 1, it is 3. And 1 plus 1 into 2, 2. And 1 into 0, 0. So you will get 1 into 2. Then 1 into 2, 2. And 1 into minus 1, minus 1. So you will get 1. And 1 into 2, 2, and 1 into minus 2, you will get plus 2 and minus 2, you will get 0. And 1 into 1, 1, and 1 into 0, 0, so you will get plus 1. Then 1 into 1 plus 1 into minus 1, you will get 0. 1 into 1 and 1 into minus 2, you will get minus 1. 1 into 0 and 1 into minus 1, you will get minus 1. 1 into 0 and 1 into minus 2, you will get minus 2. 1 into minus 1 and 1 into minus 2, you will get minus 1 plus minus 2, you will get minus 3. So there are a set of ML values we have obtained. Now we have to finally the suitable ML values are selected for respective L values as follows. You see here. Now we collect ML values for a suitable L values. You see here plus 3, plus 2, plus 1, 0. And for this you are getting there is a minus 3, minus 3, minus 2 and minus 1. So now you are getting plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3 ML values. So now we will see in the next slide what L value is assigned for these ML values. What are the left behind in the ML values are plus 1, 0, minus 1. So there are 2 set of ML values we have collected, and we see what are the L values for this. The next slide. Now you see this. Plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. So this corresponds to L value. This corresponds to L value is equal to 3, which represents F state, which represents F state. And now this already we have derived only for triplet state, so it's a triplet F. So triplet F. So we have obtained triplet F state. So already we have obtained this is a ground term in a previous presentation. How we obtained, I have already given the procedure. Now the another ML value set of ML values are plus 1, 0 and minus 1. Corresponds to L value 1. So which represents P state. So already it is a triplet state, so it is a triplet P. So now we have arrived at two triplet state, triplet F and triplet P. So for the triplet state, we have obtained two term states, triplet F and triplet P. The next, for the same D2 configurations, now we find the possible term for singlet arrangement. Singlet means anti-parallel arrangements. Anti-parallel arrangements. Now we obey the Pauli's exclusion principle as, because the two electrons can be placed in the same orbital here in the same box. So the two electrons are placed in the anti-parallel here. So these are first you see here. Now in this box diagram, the electrons are filled in anti-parallel spins as follows, obeying Pauli's exclusion principle. The two electrons can be placed in same orbital with opposite spins. As we have seen in the previous triplet arrangement, the same procedure is followed here too till all possibilities are completed. Now you see here, first we keep two electrons in the plus 2 level. The second possibility, keeping the first electron in the same plus 2 level, second electron in the opposite spin in the plus 1 level. And successive levels, we are keeping all this first electron here and the next opposite spin, anti-parallel spin in the next level, and the same one in the same plus 2 level. The second electron goes to the minus 1 in the opposite spin. The first electron is kept in the same plus 2 level. The second electron goes to the next higher level in the above the first electron in the minus 2 level, but the spins are opposite. It's anti-parallel arrangements. Next, we start the parallel spin, anti-parallel spin here. So the anti-parallel spin in this plus 1 level. Okay. Next, you are keeping here. Next, we are keeping here the first level, and the next electron goes to 0. And next, we are keeping the first electron in the same plus 1 level. The next electron goes to the minus 1 level. And by keeping the electron in the same plus 1 level, the second electron goes to this level. So next we start from the ML level 0. ML is equal to 0. The two electrons are anti-parallel in this same box, and we keep the first electron here in the same 0 level, and the next electron goes to minus 1, and keeping the first electron in the same 0 level, and the next electron goes to the minus 2 level. Next we start from the minus 1 level in the anti-parallel spins, and next keep the first electron here, and the second electron goes to the next higher level. The last possibility is only you are making these two electrons in the anti-parallel in the minus 2 level. So we have completely exhausted all possible ways of arrangement of these two electrons in the anti-parallel spins. Now we collect the suitable ML values for a particular L value. You see here is a plus 4, plus 3, plus 2, plus 1, 0, and minus 4, minus 3, minus 2, and minus 1. So plus 3, plus 4, plus 3, so plus 4, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3, minus 4. So this is a set of ML values, refers to L is equal to 4, which represents G state. And again we have to collect some suitable ML values. Here is a plus 2, plus 1, 0, minus 1, and minus 2. So you see here plus 2, plus 1, 0, minus 1, minus 2. So this refers to L is equal to 2, which represents D state. And one number is left is 0. So this number is left. So one number is left, this is 0. This which refers to L is equal to 0, which corresponds to a state. So now actually it's a singlet state. So we have obtained 3 states. They are singlet G, singlet D, singlet S. So now we have 3 singlet states. Already we have 2 triplet state, and now we have 3 singlet states for D2 configurations. So therefore all possible terms for D2 configurations are triplet F, triplet P, singlet G, singlet D, singlet S. Now we see how the terms are arranged in increasing order of their energy. There are some rules. Rule 1. If the spin multiplicity is maximum, then the energy will be minimum. This is due to the fact that when more unpaired electrons present, electron-electron repulsion will be less and stability will be more. So the energy is in the order triplet is less than doublet, which is less than singlet. So triplet F and triplet P are lower in energy among all 5 states we have obtained for D2 configurations. Then rule 2, if 2 states have same spin multiplicity, then the one with higher L value will have lower energy. This is due to the reason that availability of more space for orbital motion, which reduces the repulsion. So triplet F, because F is a higher L value than P, because F the L value for F is 3 and L value for P is 1. So triplet F is lower energy than triplet P. Rule 3. For a given value of S and L, the smallest J value, J is equal to L minus S, is the most stable if the subcell is less than half filled. The highest J value, J is equal to L plus S, is the most stable if the subcell is more than half filled. According to these rules, the term states for D2 configurations can be arranged in increasing order of their energy as follows. Triplet F is less than triplet P, is less than singlet G, is less than singlet D, is less than singlet S. So this is the increasing order of their energy for D2 configurations for the states, different states. The next, the total number of splittings for D2 configurations can be represented as follows. Now you see the table shows the microstates for each term state for D2 configurations. Finally, we arrived at total microstates for this configuration, that is equal to 45. You see in this diagram, you see there are a triplet F, because for F the degeneracy is 7, and we applying that formula already I have given. F, that is a 7 into 3, you will get 21, and P is degeneracy is 3, that is a 2L plus 1 is equal to 2 into 1 plus 1 is equal to 3. So it's a 3 into 3 is a 9. Then D is a degeneracy 5 and 1, you will get 5. And degeneracy for G is 9 into 1, you will get 9. And degeneracy for S is equal to 1 into 1, you will get 1. Totally, you will get 5 microstates. Now, we see another diagram here. From this diagram, we understand that for just 2 electrons present in d orbital, that give rise to 45 number of splitting in electronic energy level. This is clearly seen in the diagram. You see here. Here also we have represented for the D2 configurations. There are 5 states with respect to this L value and S value. There is electron-electron repulsions. So triplet F, triplet P, singlet D, singlet G, singlet S. Now this triplet F, there are 3 spin orbit coupling value. This is a triplet F 2, 3 and 4. 2, 3, 4 is the lowest value, is because it's below or is less than half filled. So the lowest J is equal to L minus value. J is equal to L minus S. So why we get this 2? J is equal to L minus S. L minus S means L is equal to SPDF 3. 3 minus S, 2 less than 2. So 3 minus 1, you will get 2. So it's J is equal to L minus S is equal to 2. And L plus S, you will get, there is 3 plus 1 is equal to 4. So that's why we are putting, and 2 means it's a minus 2 and plus 2, you will get minus 2, minus 1, 0, plus 1, plus 2. So you will get 5, you will get 5 values. And here for 3, you are getting plus 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, your total you will get 7 splittings. And for these 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, plus 4, you will get totally 9. Likewise, you are getting for this value, for this, triplet P, you are getting for triplet P0, triplet P1, triplet P2, only one 0 level is a 1 splitting, and for this you are getting 3 and 5, here again 5 and 9, and 1 totally you are getting 45 microstates. So this is the diagram represents the total microstates. This clearly seen in the diagram. There are 45 microstates. Now, determination of microstates for any electronic configuration. We can calculate the microstates for any electronic configurations by using a very important formula is given here. The formula used to calculate the microstate for any electronic configuration is given as the number of microstates is equal to n factorial divided by r factorial into n minus r factorial, where n is equal to the twice the number of orbitals. For example, if p orbital is there, is a twice the number is actually p orbitals are 3, so 2 into 3, 6. If d orbitals, there are 5 d orbitals, so 2 into 5, 10 orbitals. So n is the twice the number of orbitals. R is equal to number of electrons in that orbital. This symbol indicates the factorial. Factorial means, for example, if 5 means 5 into 4 into 3 into 2 into 1. So now we are applying this formula. We have to find out the microstates for some electronic configurations. The first example for P2 configuration. For P2, that is n is equal to 2 into 3 because of p orbital, 3 orbitals, so 2 into 3, 6. N is equal to 6. R is equal to 2. Here there are the number of electrons 2. So n minus r is equal to 6 minus 2, 4. Substitute these values in the formula. Number of microstates n factorial divided by r factorial, n minus r factorial. You are getting 6 factorial divided by 2 factorial into 4 factorial is equal to 6 into 5 into 4 into 3 into 2 into 1 divided by 2 into 1 into 4 into 3 into 2 into 1 is equal to 720 divided by 2 into 24, you are getting 15. So for P2 configuration, the number of microstates are 15. For T2 configuration, already we have derived by some methods like whole formalism. Again, we apply the formula for T2 configuration. You are getting n is equal to 2 into 5 because d orbitals are 5. So 2 into 5 is equal to 10. R is equal to 2 electrons, that is r is equal to 2. N minus r is equal to 10 minus 2 is equal to 8. Substitute these values in the formula. You are getting 10 factorial divided by 2 factorial, 8 factorial, 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1 divided by 2 into 1 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. You just cancel out these values. Here the 8, 7, 6, this you can easily cancel out here. The same values are solved. So 10 into 9, 90. 2 into 1, 2. So 90 by 2, you will get 45 microstates. So this is a very useful formula to find out the microstates for any electronic configurations. So now all possible term states with their microstates for all DN configurations are given in this table. For DN configurations, D1 and D9 both are having the same number of microstates, 10. And the possible term for this D1, D9, only one state for this D1 and D9, there is a doublet D. And D2, D8, both are having the microstates 45, and possible terms are triplet TF, triplet P, singlet G, singlet D, singlet S. And for D3, D7, 120 microstates, and other all possible terms are given in this table. And for D4, D6, the number of microstates are 210, and all possible terms are given. And for D5, the number of microstates are 252, and all possible terms are given in this table. And the last one is D10, is the number of microstates is only 1, and the possible term is only 1. That's a singlet yes. So singlet yes. So this is actually the presentation for these microstates. I think it is very useful for you because already I have given the term symbol, the presentation, the previous presentation. I have described about the term symbol. And now these are microstates. These are very useful for the electronic spectroscopic studies. And this, I hope this will be very useful for you. So thank you for watching. And I request subscribe this channel and click the bell button to receive notifications for watching more videos on advanced chemistry topics. Thank you.